What if the universe wasn't supposed to exist at all? Think about it. Every atom, every star, every breath you take hinges on a cosmic balancing act so precise that even the tiniest shift would unravel everything. Scientists call it the fine-tuning problem, and it's one of the most baffling mysteries in all of physics. Why do the fundamental constants of nature, the speed of light, the strength of gravity, the mass of an electron, have exactly the right values to allow galaxies to form, planets to orbit, and life to emerge? If any of these numbers were even slightly different, reality as we know it would collapse into chaos. Stars wouldn't ignite, atoms wouldn't hold together. The universe would be a void of nothingness. This isn't just theoretical, it's a puzzle that keeps physicists awake at night. Imagine rolling a die with 1 billion sides, and it lands on the one outcome that allows existence. That's the odds we're dealing with. Some researchers argue it's pure luck. Others whisper about multiverses, where countless failed universes flicker in and out of being, and we just happen to live in the one that worked. But there's a third, even more unsettling possibility. What if the universe shouldn't exist at all? What if the math itself points to a reality that's fundamentally impossible? That's the journey we're taking today. We'll dive into quantum fluctuations that defy logic, cosmic coincidences that border on the miraculous, and the eerie silence of a universe that seems to scream, "I shouldn't be here." From the mind-bending implications of antimatter to the enigmatic role of dark energy, we'll uncover why our existence might be the greatest statistical anomaly of all time. By the end, you'll see the cosmos in a whole new light, and maybe, just maybe, you'll start to wonder if the universe is hiding something from us, ready to question everything. Let's begin. The fine-tuning problem isn't just about numbers on a page, it's about the razor-thin edge between existence and oblivion. Take gravity, for example. If it were just a fraction stronger, all the matter in the early universe would have collapsed back in on itself, snuffing out any chance for stars or galaxies to form. But if gravity were slightly weaker, matter would have scattered too thinly, leaving the cosmos a cold, empty expanse. The same goes for the nuclear forces holding atoms together. Tweak them even a little, and you'd either end up with a universe full of nothing but hydrogen, or one where heavier elements couldn't form at all. No carbon, no oxygen, no building blocks for life. Then there's the cosmological constant, which governs the expansion of the universe. If this value were off by even 1 part in 10 to the power of 120, space would either rip itself apart too quickly for planets to form or crumple into a black hole before life had a chance to emerge. These aren't hypotheticals, they're hard limits written into the fabric of reality. Physicist Martin Rees once compared it to balancing a pencil on its tip for billions of years. The fact that we're here to observe it at all seems statistically impossible. So what's really going on? One camp argues for the multiverse, a vast, perhaps infinite, collection of universes, each with its own set of physical constants. In most of them, the numbers don't add up and existence fizzles out. But in a rare few, like ours, the conditions are just right. It's the cosmic equivalent of winning the lottery, except the odds are infinitely worse. Others propose something even stranger, that the universe isn't just finely tuned, but required to be that way. Some versions of string theory suggest the constants aren't arbitrary, but are locked in by deeper, hidden laws we haven't uncovered yet. Then there's the radical idea that the universe might be self-aware, somehow selecting its own parameters to allow observation. It sounds like science fiction, but when faced with odds this extreme, even the wildest explanations start to seem plausible. What's undeniable is that the fine-tuning problem forces us to confront a haunting question. Are we here by accident, or is the universe hiding a deeper layer of meaning? Every atom in your body, every star in the sky, exists because an unimaginably precise set of rules was followed to the letter. And that's either the most incredible coincidence in history or a clue to something far bigger than we've ever imagined. But what if the universe isn't fine-tuned for life by chance? What if it's fine-tuned because of life? That's the spine-tingling idea at the heart of the Anthropic Principle. It flips the script entirely. Instead of asking why the universe happens to allow our existence, it suggests the universe must allow our existence because we're here to observe it. Think of it like a cosmic version of the old tree falling and the forest question. If a universe exists with no one to witness it, does it even count as real? At first glance, this seems like a clever way to sidestep the fine-tuning problem. Of course, we find ourselves in a universe that permits life. We couldn't very well exist in one that doesn't. But dig deeper, and the Anthropic Principle opens a rabbit hole of paradoxes. For starters, it feels suspiciously like a circular argument, saying, the universe is this way because we're here to see it, doesn't actually explain how or why the constants ended up so perfectly balanced. It's like saying a bookshelf is sturdy because it hasn't collapsed yet. Then there's the eerie implication that consciousness might play some role in shaping reality itself. Some interpretations of quantum mechanics already suggest particles exist in a haze of probabilities until observed. So could the universe, on some fundamental level, require observers to crystallize into existence? It's a tantalizing thought, but critics argue it's less science and more philosophy dressed in a lab coat. After all, if the Anthropic Principle can explain any possible universe by saying, well, someone had to be here to see it, does it really explain anything at all? Yet there's a compelling counterpoint. The Anthropic Principle isn't meant to be a standalone answer, but a lens to narrow down possibilities. Imagine you're a detective investigating a murder, and you discover the victim was poisoned with a chemical found in only one lab in the city. You wouldn't shrug and say, well, they had to be poisoned by something. You'd use that clue to focus your search. Similarly, the Anthropic Principle helps physicists rule out universes where life is impossible, leaving us to study the rare ones where the math adds up. But here's where things get really strange. If the Anthropic Principle holds water, it hints that our universe isn't just a lucky accident, it's inevitable. That doesn't necessarily mean a higher power is pulling strings, but it does suggest existence might follow rules we don't yet understand. Maybe the constants aren't random dials but gears in a deeper mechanism. Or maybe, as some theorists speculate, consciousness and cosmos are tangled in a way we're only beginning to glimpse. The Anthropic Principle doesn't solve the mystery of why the universe exists. But it does force us to confront a humbling truth. We're not just passive observers of reality, we're part of the equation, and that changes everything. Even the vacuum of space isn't as empty as it seems. At the smallest scales, reality behaves like a rolling boil. Particles flicker into existence for fractions of a second before vanishing back into the void. These quantum fluctuations aren't just theoretical oddities, they're the universe's background static, a ceaseless dance of creation and annihilation that defies classical physics. Imagine shaking a snow globe where the flakes appear and disappear at random, except here, the flakes are entire particles and the globe is the fabric of space-time itself. This isn't just a quirk of quantum theory, it's been experimentally confirmed. The Casimir effect, where two metal plates placed incredibly close together feel an invisible force pushing them together, proves that empty space is anything but. The plates squeeze out certain fluctuations, leaving more activity outside than inside, and the pressure difference moves them. It's as if the universe is constantly whispering something from nothing. But here's the real mystery. If particles can appear spontaneously, could the entire universe have done the same? Some theories suggest our cosmos might be the ultimate quantum fluctuation, a random bubble in an infinite sea of nothingness that, against all odds, stabilized instead of vanishing. Picture a single soap bubble surviving in a storm, growing against the wind. The math even checks out. In quantum terms, the energy of the entire universe might cancel out to zero when you account for gravity's negative pull, meaning no fundamental law was broken when everything sprang from nothing. Yet this raises a haunting question. Why didn't the universe immediately collapse back into the void? Quantum particles typically vanish as quickly as they appear, but our cosmos has endured for billions of years. One clue might lie in inflation, the explosive expansion in the universe's first moments. Like stretching a rubber sheet, inflation could have smoothed quantum jitters into the vast, stable cosmos we see today. But that just pushes the puzzle back a step. What triggered inflation, and why did it last just long enough to create galaxies, but not so long that space became a featureless desert? The deeper we dig, the stranger it gets. Virtual particles, those fleeting quantum apparitions, might even hold the key to dark energy, the mysterious force accelerating the universe's expansion. Every fluctuation carries energy, and over cosmic scales, that energy could add up to the repulsive force we observe. If true, it means the same quantum froth that might have birthed the universe is now tearing it apart. So where does this leave us? Quantum mechanics paints a picture of a universe built on uncertainty, where existence itself is a precarious balancing act. The particles in your body, the light from distant stars, all of it might trace back to random flickers in the dark. Whether that's the final answer or just another layer of the mystery, one thing's certain: the universe's persistence isn't just a fact. It's a defiance of the odds. What if everything you know, every memory, every sensation, even the feeling of reading these words right now, is just a fleeting spark in the dark? That's the chilling premise of the Boltzmann brain paradox, a thought experiment that takes quantum weirdness to its logical extreme. Imagine the universe as an infinite sea of chaos, where random fluctuations occasionally spit out order like waves tossing up foam. Given enough time, shouldn't it be statistically easier for a single, fully formed brain to pop into existence complete with fabricated memories of a life it never lived, than for an entire cosmos with galaxies, planets, and billions of years of history to emerge? At first, this sounds like pure philosophical nightmare fuel, but the math is disturbingly sound. Austrian physicist Ludwig Boltzmann first floated the idea in the 19th century while wrestling with entropy, the universe's tendency toward disorder. If entropy dictates that chaos is the default state, then any organized system, whether a brain or a universe, must be a temporary deviation, and statistically, smaller deviations are far more likely than larger ones. Picture a tornado tearing through a junkyard. The odds of it randomly assembling a single working watch are slim but imaginable. The odds of it building an entire clock factory, effectively zero. So why don't physicists lose sleep over this? Some argue the paradox is a reductio ad absurdum, a sign that our theories about the universe's origins might be missing a crucial piece. If the math says you're probably a Boltzmann brain hallucinating reality, but your senses insist otherwise, maybe the math needs reworking. Others counter that the paradox evaporates if the universe truly had a beginning, like the Big Bang, rather than existing eternally. An infinite timeline allows for infinitely unlikely events, but a finite one changes the odds entirely. Yet the real sting of the Boltzmann brain isn't just its unsettling premise, it's how it exposes the fragility of our assumptions. We take for granted that our senses reflect objective reality, but science keeps revealing how slippery perception can be. From optical illusions to quantum entanglement, the universe seems determined to remind us certainty is an illusion. The Boltzmann brain takes this to the limit, suggesting even that you experiencing this moment might be a cosmic accident. But here's the twist: the paradox might actually point the way forward. If the idea of Boltzmann brains undermines our current models, perhaps it's a clue that reality operates on rules we haven't discovered yet. Some theorists propose that consciousness itself could be a fundamental feature of the universe, not just a byproduct of atoms arranging themselves. Others suggest the paradox reveals a flaw in how we calculate probabilities across infinite time and space. One thing's clear: the Boltzmann brain isn't just a quirky thought experiment. It's a mirror held up to our deepest uncertainties about existence. Whether it's a dead end or a signpost to deeper truths, it forces us to confront an unnerving possibility: that reality might not be what it seems, and the only thing we can truly trust is the question itself. We can see only a fraction of the universe, less than 5% of everything that exists. The rest is hidden in plain sight, woven into the fabric of reality, yet completely invisible to our eyes. Dark matter and dark energy aren't just gaps in our knowledge. They're the dominant forces shaping the cosmos, holding galaxies together while simultaneously pushing them apart. Without them, the universe as we know it wouldn't just behave differently, it would cease to make sense entirely. Take dark matter first. It doesn't emit, absorb, or reflect light, yet its gravitational pull is the cosmic glue keeping galaxies from spinning themselves into oblivion. Picture a merry-go-round whirling so fast that the riders should fly off, but somehow they don't. That's what dark matter does for stars on the edge of galaxies. Astronomers first noticed its effects in the 1930s when they calculated the mass of galaxy clusters and realized visible matter accounted for barely a fraction of the gravity needed to hold them together. Since then, we've mapped its presence through gravitational lensing, the way its mass bends light from distant objects like a cosmic magnifying glass. Yet after decades of searching, we still don't know what it actually is. Is it an undiscovered particle, a shadow version of ordinary matter, or something even stranger, defying the laws we thought were fundamental? Then there's dark energy, the phantom force stretching the universe apart at an accelerating rate. Discovered in the late 1990s when astronomers observed distant supernova dimmer than expected. It's the opposite of dark matter, a repulsive pressure embedded in space itself. Imagine blowing up a balloon with dots on its surface. As the balloon expands, the dots move apart. Now imagine the balloon starts inflating faster and faster on its own. That's dark energy at work, and its implications are staggering. If it continues unchecked, it could eventually tear apart galaxies, stars, even atoms in a theoretical Big Rip. What makes these invisible giants so baffling is how perfectly they balance the cosmic scales. Dark matter's gravity pulls matter together, fostering the birth of galaxies, while dark energy pushes space apart, preventing a catastrophic collapse. It's as if the universe calibrated their strengths to an impossible precision: too much dark matter, and everything would have clumped together too soon. Too much dark energy, and nothing would have clumped at all. This delicate equilibrium raises a haunting question. Are dark matter and dark energy just more examples of fine-tuning, or do they hint at a deeper layer of physics we've yet to uncover? Some theories suggest dark matter could be made of weakly interacting massive particles that barely interact with normal matter except through gravity. Others propose actions, hypothetical particles so light they behave more like waves than discrete objects. There are even wilder ideas, like dark matter being primordial black holes formed in the universe's first moments. As for dark energy, it might be the cosmological constant. Einstein once proposed a property of empty space itself, or it could be evidence of extra dimensions leaking gravity into our universe. But here's the real kicker. If dark matter and dark energy make up 95% of reality, then everything we can see, stars, planets, you and me, is just the cosmic frosting on an invisible cake. That's humbling but also exhilarating. It means the universe still holds mysteries vast enough to rewrite physics. Every time we think we've got it figured out, the cosmos reminds us the rules we know might just be the tip of the iceberg. And that's either the most unsettling thought in science or the most thrilling invitation to keep exploring. If our universe feels like a statistical impossibility, what if it's just one ticket in a cosmic lottery with infinite losers? That's the heart of the multiverse theory, a sprawling web of parallel realities, each with its own unique set of physical laws. Some might be stillborn, collapsing instantly under their own contradictions. Others could be vast, empty wastelands where gravity is too weak to form stars or atoms too unstable to bond. And then there's ours, where every constant aligns like a perfect combination lock, allowing galaxies, planets, and life to emerge. At first glance, the multiverse seems like an elegant solution to the fine-tuning problem. If there are countless universes, each a roll of the dice, then it's no surprise at least one hit the jackpot. Think of it like a cosmic casino where the house always wins, but winning means a universe can support conscious observers. The math even checks out in some versions of string theory, which suggests the fabric of reality could have 10 to the power of 500 possible configurations. That's a 1 followed by 500 zeros, a number so vast it makes the atoms in our observable universe seem paltry in comparison. But here's the catch: if the multiverse is real, how could we ever prove it? Critics argue it's less a scientific theory and more a philosophical shrug, an untestable idea that explains everything and nothing at once. Imagine a detective saying, "There must be infinite crime scenes somewhere, and we just happen to live in the one where the evidence makes sense." It's a dizzying thought, but does it actually advance our understanding? Some physicists counter that certain versions of the multiverse could leave fingerprints like gravitational echoes from collisions between neighboring universes in the early cosmos. Others suggest the patterns in the cosmic microwave background, the afterglow of the Big Bang, might reveal subtle anomalies where the rules of our universe brush against others. Yet, even if we never find direct evidence, the multiverse forces us to confront a radical possibility. Our existence might not be special, just inevitable. In an infinite ensemble of universes, every conceivable outcome, no matter how improbable, must happen somewhere. There could be realities where light travels slower, where time runs backward, or where the laws of physics rewrite themselves daily. The unsettling implication: we're not the protagonists of the cosmos, just random winners in a game with no rules. But there's another twist. If the multiverse is real, it might not be the cosmic free-for-all it seems. Some theories propose these universes aren't entirely disconnected but branch from each other like tendrils of a vast, growing vine. Quantum mechanics already hints at this with the many worlds interpretation, where every decision spawns a new timeline. In this view, the multiverse isn't just a collection of alien realities. It's a living, breathing fractal of possibilities, with every choice you don't make playing out somewhere else. So where does that leave us? The multiverse might be a brilliant workaround for the fine-tuning problem, or it might be a placeholder for deeper truths we've yet to uncover. Either way, it shatters the illusion that our universe is the only show in town. And that realization, whether it's science's greatest leap or its most elaborate guess, changes how we see our place in the grand scheme of things. Maybe we're not here against the odds. Maybe, in the grandest sense, the odds were always in our favor. The Big Bang wasn't just the beginning, it was the ultimate cosmic magic trick. In an instant, all the energy, matter, and space we know erupted from a singularity smaller than an atom. But here's the catch. The Big Bang Theory explains how the universe expanded, not why it happened in the first place. It's like walking into a movie halfway through and trying to guess the plot from the explosion on screen. So what could have sparked it? One leading idea points to quantum vacuum fluctuations, the same eerie phenomenon that allows particles to blink in and out of existence. If randomness can spawn particles, maybe it could spawn an entire universe. Picture a bubble forming in a pot of boiling water, but instead of steam, it's space-time itself. In this scenario, our cosmos might be one bubble in an endless froth of universes, each with its own physics. Yet even this raises deeper questions. Quantum fluctuations rely on pre-existing laws, rules governing probabilities and energies. So where did those come from? Some theorists propose a quantum gravity framework, where time and space themselves emerge from something more fundamental, like strands in a cosmic tapestry. Others explore the idea of a big bounce, where our universe is just the latest cycle in an eternal sequence of expansions and contractions, a cosmic heartbeat. Then there's the wild card. What if the Big Bang wasn't the start at all? Certain interpretations of string theory suggest our universe could be a four-dimensional brain colliding with another in a higher dimensional space. Imagine two sheets of paper smacking together in a dark room. The energy of that impact might have ignited everything we see. It's speculative, but it hints at a reality far stranger than we've imagined. The real puzzle isn't just the lack of answers, it's the lack of questions we can even ask. Without time or space before the Big Bang, concepts like cause and before might not apply. Physics as we know it hits a wall at the singularity, leaving us staring into the unknown. Maybe the truth lies beyond our current math, waiting for a paradigm shift as radical as relativity was to Newton. One thing's certain, the Big Bang's origins aren't just a gap in knowledge, they're a doorway. Whether it leads to multiverses, higher dimensions, or something beyond human intuition, the mystery reminds us that the universe is far weirder and more wondrous than we've dared to dream. The universe is running out of steam every second in ways we can't see. It's slipping closer to a state of total equilibrium, a cold, silent end where all energy dissipates, stars burn out, and even black holes evaporate into nothingness. Scientists call it heat death, the ultimate victory of entropy, the law that says disorder always increases. Yet here we are in a universe teeming with galaxies, planets, and life, all defying the odds like a candle refusing to melt in a furnace. How does existence keep dancing on the edge of collapse? Entropy isn't just a scientific concept, it's the universe's expiration date. Picture a cup of hot coffee left on a table. Over time, the heat disperses into the air until both the coffee and the room reach the same lukewarm temperature. No energy is lost, but it's now useless, unable to do work. Now imagine that same principle applied to the entire cosmos. Given enough time, trillions upon trillions of years, every star will exhaust its fuel, every particle will spread out, and the universe will become a featureless void. The math is clear, entropy always wins, but here's the paradox. If disorder always increases, how did we end up with a universe so full of structure? Think about Earth, a speck of order in the chaos. Water cycles between oceans and clouds, plants convert sunlight into energy, and your body rebuilds cells faster than they decay. These aren't just happy accidents, they're localized rebellions against entropy, pockets where complexity thrives. The secret lies in energy gradients. The sun, a nuclear furnace, pours out photons that Earth captures, creating a temporary imbalance that life exploits. It's like a waterfall powering a mill. The water's downward flow is a gradient that does work before leveling out. On a cosmic scale, the Big Bang created the ultimate gradient, a fiery explosion of concentrated energy that's still dispersing today. Yet even this doesn't fully explain life's persistence. The real mystery is why the universe didn't rush straight to equilibrium. One clue comes from gravity. While entropy pushes things apart, gravity pulls them together, creating new pockets of order. Stars form when gas clouds collapse, galaxies cluster in vast webs, and black holes warp spacetime into knots of extreme concentration. Gravity, in a sense, fights entropy's spread, turning the universe into a battleground between dispersion and cohesion. But gravity alone can't stave off heat death forever. Eventually, even the most massive black holes will radiate away their energy, leaving behind a sea of particles too distant to interact. That's where the paradox deepens. If the universe is doomed to stillness, why does it feel so alive right now? Some theorists suggest we're living in a Goldilocks era, a brief window where the conditions for complexity are just right, not too soon after the Big Bang when everything was scorching plasma, and not too late when everything's frozen and dark. Others propose a more radical idea, that the universe isn't just a one-way slide into chaos but part of a cycle where new universes bud off from the remnants of old ones. The heat-death paradox forces us to confront a humbling truth. Our existence isn't just improbable, it's ephemeral, a flicker of order in an ocean of entropy. Yet that fleeting nature makes it all the more astonishing. Every galaxy, every heartbeat, every thought is a defiance of the universe's slow unraveling. Whether that defiance is temporary or part of some deeper pattern remains one of cosmology's greatest unanswered questions. But one thing's certain, the fact that we're here to ask it at all is nothing short of miraculous. Symmetry is the silent architect of the universe, shaping everything from the spin of an electron to the spiral arms of galaxies. At first glance, it seems like perfection, a snowflake's delicate balance, the mirrored wings of a butterfly, the way a circle looks identical no matter how you rotate it. But here's the twist. If symmetry were absolute, the universe as we know it wouldn't exist at all. Take the laws of physics themselves. They're remarkably symmetrical in their purest form. Flip a particle's charge, reverse time, or mirror its position, and the equations still hold. This elegance is more than just mathematical beauty. It's a clue to how reality operates at its core. Yet something strange happened in the early cosmos. During the first fractions of a second after the Big Bang, symmetry broke. Like a vase shattering into pieces, the universe's pristine balance fractured, and those cracks might be the reason you're here to ponder them. One of the most dramatic examples is the matter-antimatter imbalance. According to theory, the Big Bang should have produced equal amounts of matter and antimatter particles, and their mirror image opposites. When matter and antimatter meet, they annihilate in a flash of energy. So why didn't the universe cancel itself out immediately? The answer lies in a tiny asymmetry, a 1 in a billion preference for matter over antimatter. Scientists call this charge parity violation, and it's been observed in particles called kaons and B mesons, which decay slightly differently than their antimatter counterparts. Without this minuscule breaking of symmetry, the cosmos would be a sea of radiation with no stars, no planets, and no life. But symmetry breaking isn't just a relic of the past, it's happening right now. The Higgs field, which gives particles their mass, is a perfect example. In its symmetrical state, all particles should be massless, zipping around at the speed of light. But the Higgs field froze into an asymmetrical state as the universe cooled, like water turning to ice. This phase transition gave rise to the hierarchy of masses we see today, from featherweight neutrinos to the hefty top quark. Without this cosmic imbalance, atoms wouldn't form, chemistry wouldn't work, and life as we know it would be impossible. Even the structure of the universe owes its existence to symmetry breaking. In the primordial plasma, quantum fluctuations, tiny ripples of asymmetry, were stretched to cosmic scales during inflation. These imperfections became the seeds for galaxies, the scaffolding of the cosmos. If the early universe had been perfectly smooth, matter would have spread uniformly, and the night sky would be a featureless void. Instead, we have a tapestry of stars, planets, and nebulae, all tracing back to those initial cracks in symmetry's mirror. So why does symmetry break at all? Some theories suggest it's a natural consequence of cooling, like how water forms hexagonal ice crystals instead of staying a uniform liquid. Others propose deeper mechanisms tied to undiscovered particles or forces. Whatever the cause, the lesson is clear: perfection is sterile. It's the flaws, the asymmetries, the breaks in the pattern that make reality rich, dynamic, and alive. The next time you marvel at a butterfly's wings or the spiral of a galaxy, remember, their beauty isn't just in their symmetry, but in how they twist it, bend it, and make it their own. The universe isn't a flawless equation, it's a masterpiece of controlled chaos, and every atom in your body is proof. Antimatter isn't just science fiction, it's the universe's greatest disappearing act. According to every equation we have, the Big Bang should have created matter and antimatter in perfect, symmetrical amounts. Yet when these twin particles meet, they annihilate in a burst of pure energy, leaving nothing behind. So why does anything still exist? The fact that we're here at all means something tipped the cosmic scales, favoring matter by the slimmest margin, just one extra particle for every billion annihilations. That tiny excess is the reason stars burn, planets orbit, and you can take your next breath. The search for this missing asymmetry has led physicists down some bizarre rabbit holes. Take the humble electron, for example. Its antimatter counterpart, the positron, has the same mass but opposite charge. When they collide, they vanish. But here's the catch. If antimatter truly mirrored matter in every way, the universe should have cancelled itself out instantly. The fact that it didn't suggests a fundamental crack in nature's mirror. This crack first revealed itself in 1964, when physicists studying kaon's short-lived particles found they decayed slightly differently than their antimatter versions. It was like flipping a coin and discovering it lands on heads 51 times out of 100 instead of 50. That 1% discrepancy sent shockwaves through physics, earning its discoverers a Nobel Prize. Later experiments with B mesons confirmed the imbalance, but the numbers still don't add up. The asymmetry we've measured is far too small to explain the overwhelming dominance of matter in today's universe. So where's the rest of the antimatter? Some theories suggest it might still be out there, hiding in vast, invisible regions of space where antistars and antiplanets could exist. But telescopes have yet to spot the telltale gamma-ray flashes that would mark antimatter annihilation on cosmic scales. Others propose that antimatter didn't vanish, it transformed. Neutrinos, the ghostly particles that stream through your body by the trillions every second, might hold the key. If neutrinos and antineutrinos behaved differently, they could have tilted the balance in matter's favor during the universe's first seconds. Then there's the wild card. What if antimatter isn't the opposite of matter at all? Some experiments hint that antiparticles might respond ever so slightly differently to gravity, falling up instead of down. It's a radical idea and no one's proven it yet, but if true, it would rewrite our understanding of the universe's deepest symmetries. The mystery of antimatter isn't just academic, it's existential. Every atom in your body exists because nature played a trick on itself, breaking its own rules just enough to leave a universe behind. And that's either the most fortunate accident in history or a clue that reality is far stranger than we've dared to imagine. Time flows like a river, always forward, never backward. You can turn left or right, but you can't reverse the current. Yet here's the strange part. The fundamental laws of physics don't actually care which way time goes. Equations for gravity, electromagnetism, even quantum mechanics work just as well whether time runs forward or backward. So why does our universe have such a stubborn one-way street? The answer might lie in entropy, the same force pushing the cosmos toward heat death. Think of a deck of cards, shuffle it, and the cards scatter into disorder, a high entropy state. Now imagine watching a video of that shuffle in reverse. The cards magically rearrange themselves into perfect order. You'd instantly know the video was running backward because in our everyday experience, order doesn't spontaneously rebuild itself. That's the arrow of time in action. The universe started in an incredibly low entropy state, a highly ordered speck of near-perfect symmetry during the Big Bang, and has been unraveling ever since. This relentless march toward disorder is what gives time its direction. But why did the universe begin with such low entropy to begin with? That's where things get eerie. Some physicists argue the Big Bang's low entropy state is the ultimate statistical fluke. Imagine a room filled with air molecules. By pure chance, all the molecules could suddenly rush to one corner, leaving a vacuum everywhere else. It's technically possible, just unimaginably unlikely. The Big Bang might have been that one in a Googleplex cosmic accident, setting the stage for time's irreversible flow. Others suggest a deeper principle is at work. If the multiverse is real, perhaps our universe's low entropy beginning was inevitable, a natural consequence of some larger, unseen physics. Then there's the quantum twist. At microscopic scales, particles don't always play by time's rules. Certain quantum processes, like the decay of a kaon particle, show tiny asymmetries between past and future. It's as if the universe whispers a faint preference for forward time, even in its smallest building blocks. Could these quantum hints be the seeds of time's arrow, amplified to cosmic scales? Or do they point to something even stranger, like time itself emerging from a timeless quantum foam? The most radical idea, time might not be fundamental at all. Just as temperature arises from the motion of particles, time could be an illusion created by the way we perceive change. In this view, the universe is a static, four-dimensional block where past, present, and future all exist simultaneously. Our sense of time's flow would just be a trick of consciousness, like a movie creating motion from still frames. Whether time is real or emergent, its one-way nature is woven into everything we experience, from the aging of stars to the firing of neurons in your brain. It's the reason memories exist but prophecies don't, why broken eggs don't reassemble themselves, and why you can't unburn a log. The arrow of time isn't just a feature of the universe. It might be the very reason the universe can exist at all. Without it, cause and effect would crumble, and reality as we know it would dissolve into chaos. So the next time you check your watch, remember, you're not just tracking hours, you're witnessing one of the cosmos' deepest mysteries. What if everything you see, the stars, the planets, even your own hands, is nothing more than a cosmic mirage? That's the mind-bending premise of the holographic principle. A theory that suggests our three-dimensional reality might be nothing more than a projection from a two-dimensional surface, like a movie playing on the walls of the universe. Imagine the entire cosmos as a hologram, where every event, every particle, even the passage of time, is just information painted onto a distant boundary we can't see. It sounds like science fiction, but this idea emerges from some of the most cutting-edge physics of our time, including black hole thermodynamics and string theory. The story starts with black holes, those cosmic vacuum cleaners whose gravity is so strong even light can't escape. In the 1970s, physicist Jacob Bekenstein discovered something astonishing. A black hole's entropy, a measure of its disorder, is proportional not to its volume as you'd expect, but to its surface area. It's as if all the information about what falls into a black hole isn't lost inside but is smeared across its event horizon, the point of no return. Later, Stephen Hawking showed black holes slowly evaporate, radiating energy until they vanish. But if information can't be destroyed, where does it go? The holographic principle offers a radical solution. The information isn't inside the black hole at all. It's encoded on its surface like a celestial DVD storing the data for the 3D movie we call reality. Take this idea further, and the implications are staggering. If a black hole's interior can be described entirely by information on its boundary, could the same be true for the entire universe? Some theorists argue yes, that everything we experience, from the birth of galaxies to the firing of neurons in your brain, might be a projection from a vast, hidden surface at the edge of spacetime. Picture a soap bubble. The shimmering colors on its surface aren't really there. They're interference patterns created by light reflecting off the bubble's thin film. In the same way, the holographic principle suggests the solidity of the world around us could be an illusion, a kind of cosmic sleight of hand where depth and dimension emerge from flat, encoded data. But how could this possibly work? One clue comes from the way information behaves at tiny scales. Quantum mechanics tells us particles are fundamentally fuzzy, existing in multiple states until measured. String theory, meanwhile, describes reality as vibrating strings in 10 or 11 dimensions, most of them curled up too small to see. The holographic principle bridges these ideas, proposing that the extra dimension string theory requires might not be out there, but could instead be hidden in the way information is processed on a lower dimensional surface. It's like how a 3D image can emerge from a 2D holographic plate. The depth isn't real, but the illusion is perfect. If this is true, it could solve some of physics' biggest headaches. The holographic principle might reconcile quantum mechanics and gravity, two theories that have stubbornly refused to unify. It could also explain why the universe appears finely tuned for life, not because of some cosmic designer, but because the rules of our 3D reality are just the way information gets translated from a 2D code. Even the Big Bang might look different through this lens, not an explosion in space, but a rendering of data on an unimaginably vast cosmic screen. Of course, the holographic principle isn't without its critics. Some argue it's more mathematical metaphor than physical reality, a useful tool for calculations but not a literal description of the universe. Others point out that if we're living in a hologram, there should be detectable pixelation at extremely small scales, a granularity to spacetime itself. Experiments like the holometer at Fermilab have searched for this effect, but so far, the universe's resolution appears flawless. Whether the holographic principle holds up or not, it forces us to confront a profound question. What is reality, really? If the solidity of the world is just an emergent property of information, then existence might be far stranger and more interconnected than we ever imagined. The universe could be less a thing and more a story, one written in a language we're only beginning to decipher. And if that's true, then the next chapter might reveal secrets even more astonishing than we've dared to dream. What if our universe isn't the base reality, but an elaborate simulation, a cosmic video game run by an advanced civilization? The idea sounds ripped from science fiction, but in recent years, it's been taken seriously by some of the sharpest minds in physics and philosophy. Even Elon Musk has famously claimed the odds we're living in base reality are 1 in billions. At first glance, it seems absurd, but when you peel back the layers, the simulation hypothesis offers a chillingly elegant solution to the fine-tuning problem. If the universe is a programmed construct, its seemingly perfect constants aren't miraculous, they're just the settings some advanced coder dialed in. The argument hinges on 3 unsettling pillars. First, if civilizations eventually develop the power to create hyper-realistic simulations, ones indistinguishable from reality, then statistically, the number of simulated minds would vastly outnumber real ones. Think of it like video games. If future humans create billions of virtual worlds, the chance you're in the original universe shrinks to near zero. Second, our own technological trajectory hints at this possibility. We've gone from Pong to photorealistic VR in 50 years. Given another 1,000 or million, could we simulate entire universes? Third, the universe behaves suspiciously like an optimized system. Quantum mechanics shows reality only renders when observed, like a video game loading textures as you explore. Even the speed of light could be a processing limit, preventing the simulation from lagging. But here's where things get thorny. If we're in a simulation, who's running it? Are we someone's ancestor simulation, a school project for alien undergrads, or glitches in a long-forgotten program? And what happens if we try to hack the system? Some physicists have proposed real-world tests, like searching for pixelation in the fabric of spacetime or anomalies in high-energy particle collisions that might reveal the universe's underlying code. Others argue the simulators would patch any bugs before we notice, like a game developer hotfixing exploits. The most haunting question isn't technical, though it's existential. If we're simulations, do our choices matter? Is free will just an illusion coded into our algorithms? Philosopher Nick Bostrom, who formalized the simulation argument, suggests it might not change anything. Even in a simulation, pain and joy would feel real to us, but others counter that it undermines meaning itself. Why strive, create, or love if we're just lines in someone else's software? Yet the simulation hypothesis isn't purely nihilistic. It could explain cosmic mysteries dark matter fails to, like quantum entanglements, spooky action at a distance. Or what if it's just data being shared between processes? It might even offer a form of immortality. If consciousness can be uploaded, death could be a logout screen. Whether the hypothesis holds water or not, it forces us to confront how little we truly know about reality's nature. The universe's fine-tuning might not be a puzzle to solve, but a clue, a breadcrumb left by creators, or perhaps just a strange loop in the logic of existence. Either way, it's a reminder that the deepest truths might lie not in the stars, but in the unseen architecture of reality itself. And that's a mystery worth chasing, simulated or not. Nothingness might seem like the simplest state imaginable. No stars, no atoms, not even empty space, just pure, unbroken void. But here's the catch: true nothingness might not exist at all. Even the emptiest vacuum we can create still crackles with quantum activity, particles flitting in and out of existence like sparks in the dark. So why is the universe so allergic to nothing? Philosophers like Leibniz and Heidegger wrestled with this question for centuries. Leibniz famously asked, "Why is there something rather than nothing?" A puzzle that feels more like a koan than a scientific inquiry. But modern physics reveals something startling. The concept of absolute nothingness might be a fantasy. Even if you could remove every particle, every wave, every trace of energy from a region of space, you'd still be left with the fabric of spacetime itself, a stage with no actors, but a stage nonetheless. And according to quantum field theory, that stage is never truly still. Virtual particles pop into existence, borrowing energy from the void before vanishing again, as if the universe has a fundamental restlessness baked into its bones. This raises a deeper question. Could a state of true nothingness ever have existed? Some theories suggest that nothing is inherently unstable, a house of cards waiting to collapse into something. Think of it like a perfectly still pencil balanced on its tip. The slightest tremor sends it tumbling. In the same way, quantum fluctuations might make nothingness a theoretical impossibility, ensuring that any attempt at perfect void inevitably births particles, energy, or even entire universes. Then there's the wild card of dark energy, the mysterious force accelerating the universe's expansion. Empty space isn't truly empty, it's seething with this latent energy, stretching the cosmos apart. If you could drain a region of space of all matter and radiation, dark energy would still be there, an unshakable residue. It's as if the universe has a built-in aversion to nothingness, a cosmic no vacancies sign etched into the laws of physics. But the most mind-bending possibility is that nothingness and somethingness might be two sides of the same coin. In quantum mechanics, particles can emerge from seemingly nowhere, their existence tied to probabilities rather than concrete causes. The Big Bang itself might have been a quantum fluctuation on an unimaginable scale, a random burp in the void that, against all odds, stabilized into everything we know. If that's true, then nothingness isn't just unstable, it's creative, a forge where universes are born from sheer unpredictability. So where does that leave us? The problem of nothingness might not have a neat answer, but it forces us to confront the strangeness of existence itself. The universe isn't just here, it's persistent, resisting emptiness with every quantum flicker and cosmic expansion. Whether that's a fluke or the signature of something deeper, one thing's certain: nothingness is anything but simple. Quantum entanglement isn't just strange, it's a cosmic magic trick that defies everything we thought we knew about reality. Imagine two coins flipped on opposite sides of the universe, yet somehow always landing on the same face. That's entanglement in a nutshell. Particles linked so intimately that changing one instantly affects its partner, no matter how far apart they are. Einstein famously dismissed this as spooky action at a distance, a phrase that captures both his skepticism and the sheer weirdness of the phenomenon. But here's the thing, it's not just spooky. It's real, verified by countless experiments, and it might hold the key to understanding how the universe stays so eerily coordinated. Take the classic example of entangled photons. If you measure one and find it spinning clockwise, its twin will always spin counterclockwise, even if it's halfway across the galaxy. This happens faster than light could travel between them, seemingly breaking the universe's speed limit. It's as if space and distance don't matter, as though the particles are whispering to each other through some hidden backchannel. Physicists call this non-locality, and it shatters the classical idea that objects can only influence each other through direct contact or forces. But how does it work? One possibility is that entangled particles aren't truly separate at all. In quantum mechanics, they're described by a single mathematical equation, a shared state that treats them as a unified system, no matter how far apart they drift. It's like tearing a piece of paper in two. The halves might be miles apart, but they're still part of the same original sheet. This interconnectedness suggests that reality, at its deepest level, might be far more woven together than we perceive. Some theorists take this even further, proposing that entanglement could be the glue holding the universe together. Think of space-time as a vast network, with entangled particles acting like invisible threads stitching it into coherence. Without these quantum links, reality might dissolve into chaos, like a tapestry unraveling at the seams. There's even speculation that entanglement plays a role in the universe's fine-tuning, that the delicate balance allowing life to exist isn't just luck, but a consequence of countless particles communicating across the cosmos to maintain equilibrium. Then there's the wilder frontier. Quantum entanglement might hint at higher dimensions or a reality beyond spacetime. String theory suggests entangled particles could be connected through extra-dimensional shortcuts, like wormholes threading through the fabric of the universe. It's a radical idea, but it bridges quantum mechanics and gravity, two theories that otherwise refuse to play nice. Of course, not everyone's convinced. Critics argue that entanglement doesn't transmit information faster than light, so it can't be used for real-time communication. Others propose hidden variables, unknown properties set at the moment of entanglement that predetermine the particle's behavior. But decades of experiments, from Bell tests to recent loophole-free verifications, keep pointing to one conclusion: entanglement is as real as it is bizarre. Whether it's a cosmic quirk or a clue to deeper truths, one thing's certain: quantum entanglement forces us to rethink the very nature of reality. The universe isn't just a collection of isolated objects. It's a dynamic, interconnected web where particles dance in perfect, inexplicable sync. And that's either the most unsettling or the most beautiful fact about existence, depending on how you look at it. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing trillions of stars, many orbited by planets in the so-called Goldilocks zone where life could thrive. Given those numbers, the cosmos should be buzzing with civilizations, their signals crisscrossing the void like a cosmic internet. Yet when we point our telescopes at the stars, all we hear is silence. This eerie absence is the heart of the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" One explanation is that intelligent life is vanishingly rare. Earth might be a cosmic fluke, a one in a quintillion accident where every variable plate tectonics, Jupiter's protective role deflecting asteroids, even the moon's stabilizing influence on our climate, lined up just right. Even if simple life is common, the leap to intelligence could be astronomically unlikely. After all, dinosaurs ruled Earth for over 100 million years without inventing radio telescopes. Maybe intelligence isn't an evolutionary inevitability, but a freak outlier. Then there's the darker possibility. The universe is a graveyard. Civilizations might arise, only to be snuffed out by cosmic catastrophes, gamma-ray bursts, supervolcanoes, or their own self-destructive tendencies. Imagine a galaxy littered with the ruins of civilizations that burned too bright, too fast. We might be alone not because life is rare, but because survival is nearly impossible. The Great Filter hypothesis suggests some catastrophic bottleneck lies ahead, or behind us, a hurdle so deadly that almost no civilization crosses it. If it's behind us, we're lucky. If it's ahead, we're doomed. But silence could also mean we're looking the wrong way. Advanced civilizations might communicate in ways we can't detect, using neutrino beams or quantum entanglement instead of radio waves. Or perhaps they're deliberately hiding, wary of attracting attention in a universe where predators lurk. Some theorists even propose we're living in a cosmic zoo, intentionally isolated by beings who want us to evolve undisturbed. The most unsettling answer: we're early. The universe is 13.8 billion years old, but it's still in its infancy. Most stars won't form for trillions of years. If intelligence tends to emerge in the far future, we might be the first or among the first. To ask these questions, the Fermi Paradox isn't just about aliens. It's a mirror reflecting our own fragility. Every scenario, whether we're alone, doomed, or simply premature, forces us to confront how little we understand about life's place in the cosmos. The silence isn't empty, it's a question echoing across the void, waiting for an answer. Black holes aren't just cosmic vacuum cleaners, they're the ultimate paradox machines. According to Einstein's general relativity, anything that crosses a black hole's event horizon is gone forever, crushed into a singularity where the laws of physics break down. But quantum mechanics, the rulebook for the very small, insists that information can never truly be destroyed. It might get scrambled, hidden, or transformed, but it should always be recoverable in principle. This clash isn't just academic, it's a battle for the soul of physics, and the stakes couldn't be higher. If information really vanishes in a black hole, our understanding of reality might need a complete rewrite. Take a book tossed into a black hole. In Einstein's universe, it's shredded by gravity, its atoms compressed into oblivion, all the words, the stories, the meaning gone. But quantum mechanics says no. The information in that book might be encoded in the black hole's radiation or etched onto its surface like a cosmic hard drive. The problem, these two theories, both wildly successful in their own domains, can't agree on what happens next. Stephen Hawking first highlighted this contradiction in the 1970s when he calculated that black holes slowly evaporate, emitting radiation until they vanish entirely. If the hole disappears, where does the information go? Hawking initially thought it was lost forever, a conclusion that horrified quantum physicists. The debate took a dramatic turn in the late 1990s when theorists proposed the holographic principle, the idea that all the information swallowed by a black hole isn't trapped inside, but is instead smeared across its event horizon like a hologram. Picture a library where every book ever burned is somehow preserved in the ashes. This would mean the universe has a built-in backup system, ensuring no data is ever truly erased. Later, Hawking changed his mind, conceding that information might escape after all, encoded in the radiation black holes emit. It's as if the universe has a cosmic recycling program, turning lost data into something new. But the mystery doesn't end there. If information escapes, how? Some theories suggest black holes might have soft hair, infinitesimally subtle imprints on their boundaries that store data like grooves on a vinyl record. Others propose that entangled particles straddling the event horizon could act as quantum teleporters, shuttling information back out. Then there's the radical idea that black holes don't evaporate completely but leave behind remnants, tiny, indestructible kernels containing all the information they ever swallowed. The most mind-bending possibility, black holes might not be the end of information but a transformation point. Just as a scrambled egg can't easily become whole again, the information inside a black hole could be so thoroughly mixed that it's effectively lost, not because it's gone, but because piecing it back together would require solving a quantum puzzle of unimaginable complexity. This is the firewall paradox, the idea that the event horizon might be a seething wall of energy, annihilating anything that touches it while preserving the information in its aftermath. Why does any of this matter? Because the information paradox isn't just about black holes, it's a proxy war for a much bigger fight. How to reconcile quantum mechanics and gravity. Solving it could crack open the door to a theory of everything, a single framework explaining reality from the smallest particles to the largest galaxies. Every proposed solution, from holography to wormholes, hints at a universe far stranger than we've imagined. So the next time you gaze at the night sky, remember, black holes aren't just swallowing stars. They're swallowing the rules of reality itself, and what they spit back out might change everything we know. String theory doesn't just rewrite the rules of reality, it shatters our perception of space itself. Imagine the universe as a symphony where every particle is a vibrating string, and the notes it plays determine whether it's an electron, a quark, or a photon. But here's the catch: these strings don't dance in the 3 dimensions we know. They need at least 6 more, curled up so tightly that even the most powerful microscopes couldn't spot them. It's like tuning a guitar with extra strings hidden inside the neck. You can't see them, but they're essential to the music. So where are these extra dimensions? Think of a garden hose. From a distance, it looks like a simple line, one dimension. But up close, you see it's a cylinder with a circular dimension wrapped around its length. In the same way, our 3-dimensional space might be threaded with microscopic loops and folds, dimensions coiled smaller than an atom. These hidden structures could explain why gravity feels so weak compared to other forces. It might be leaking into other dimensions, diluting its strength like water seeping through a sieve. But why would nature need all these dimensions? The answer lies in stability. String theory suggests that most configurations of dimensions would collapse instantly, like a house of cards in a hurricane. Only a rare few, like our 3D universe with its 6 or 7 tightly curled companions, can endure long enough for galaxies and life to form. It's as if the cosmos is a vast library of failed drafts, and we're living in the one story where the math doesn't implode. Some theorists take this further, proposing that these extra dimensions aren't static but dynamic. They could be constantly shifting, with some universes expanding their hidden dimensions while others squeeze them shut. In this view, our universe's stability isn't just luck. It's a fleeting equilibrium, like a spinning top that hasn't wobbled over yet. Then there's the wildest idea of all. What if these dimensions aren't entirely hidden? Certain versions of string theory predict that if we could probe small enough, way beyond the reach of current particle colliders, we might find evidence of higher dimensional resonances, like echoes from a parallel wall. Experiments searching for tiny deviations in gravity at microscopic scales could, in theory, stumble upon these fingerprints. The deeper we dig, the clearer it becomes. String theory's extra dimensions aren't just mathematical quirks. They might be the cosmic scaffolding holding reality together, the reason our universe exists while countless others failed. And if that's true, then every atom in your body isn't just a particle, it's a vibration in a hidden, multidimensional symphony. Earth sits in a cosmic sweet spot, not too close to the sun, not too far, with just the right conditions for water to flow and life to thrive. But what if our entire universe is also sitting in a Goldilocks zone of its own? Not a place in space, but a razor-thin balance in the laws of physics themselves. Tweak the strength of gravity by a fraction, adjust the charge of an electron by a hair, and existence as we know it would blink out like a candle in a hurricane. The universe shouldn't work, and yet here we are. Take the strong nuclear force, the glue holding atomic nuclei together. If it were just 5% weaker, protons and neutrons wouldn't bond, and hydrogen would be the only element in the cosmos. No stars, no planets, no chemistry. But if it were slightly stronger, atoms would fuse too easily, burning up all their fuel in seconds. The universe would be a flash in the pan, literally. It's not just the forces either. The masses of fundamental particles are equally precarious. An electron's mass is fine-tuned to allow stable atoms. If it were much heavier, molecules couldn't form. If lighter, chemical reactions would grind to a crawl. Life isn't just riding the edge of possibility, it's dancing on a tightrope strung across the void. Then there's the cosmological constant, the value governing how fast empty space expands. When Einstein first proposed it, he called it his greatest blunder, but modern cosmology shows it's very real and impossibly precise. If this number were a hair larger, the universe would have expanded too quickly for galaxies to form. A hair smaller, and gravity would have pulled everything back into a cosmic crunch billions of years ago. The margin for error, something like 1 part in 10 to the power of 120, that's a number so small it's hard to fathom, like randomly hitting a single atom in the observable universe while blindfolded. This isn't just numerology. The fine-tuning shows up in experiment after experiment. Even the ratio of matter to antimatter in the early universe, a 1 in a billion imbalance, had to be exact or we wouldn't be here. So how do we explain this cosmic luck? One possibility is the multiverse, a vast ensemble of universes, each with randomly dialed constants, and we just happen to live in the one where the numbers worked out. It's the ultimate survivor bias. If the constants were different, no one would be around to notice. But there's another, even stranger idea. What if the universe isn't lucky but inevitable? Some theories suggest the laws of physics aren't arbitrary but emerge from deeper, self-consistent principles. Like a snowflake forming in cold air, the universe might take the shape it does because no other shape is possible. In this view, the Goldilocks zone isn't an accident, it's the only game in town. Whether by chance or necessity, the universe's precarious balance forces us to confront a humbling truth. Existence is far more fragile than it seems. The stars above, the ground beneath your feet, all of it hangs in a delicate equilibrium, a cosmic tightrope walk where one misstep means oblivion. And that's either the most terrifying thought imaginable or the most miraculous. The quantum world operates on a different set of rules than the one we experience every day. At the subatomic level, particles don't behave like tiny billiard balls with fixed positions and speeds. Instead, they exist in a haze of possibilities, a superposition of states until someone or something takes a measurement. It's as if reality itself hesitates, refusing to commit to a single outcome until forced to do so. This is the observer effect, one of the most mind-bending and hotly debated concepts in quantum mechanics. Take the classic double-slit experiment. When particles like electrons are fired at a barrier with 2 slits, they don't just go through one or the other. They behave like waves, creating an interference pattern on the other side, as if each particle passes through both slits simultaneously. But here's where it gets strange. If you place a detector to observe which slit the electron actually goes through, the interference pattern disappears. The mere act of looking collapses the wave function, forcing the particle to choose a single path. It's as if reality reshapes itself under scrutiny, shifting from potential to concrete the moment it's observed. This phenomenon isn't limited to lab experiments. Quantum systems all around us, from the electrons in your phone's circuitry to the photons streaming from distant stars, seem to play by these rules. The unsettling implication: reality might not be a fixed stage waiting for us to uncover it, but something that actively crystallizes in response to observation. This blurs the line between the observer and the observed, raising a radical question. Does consciousness itself play a role in shaping the universe? Some interpretations of quantum mechanics, like the Copenhagen interpretation, argue that measurement is what defines reality. Without an observer, there's no definitive state, just probabilities. Others, like the von Neumann-Wigner interpretation, take it further, suggesting that consciousness is the ultimate tool that collapses the wave function. In this view, the universe isn't just seen, it's created by the act of observation. Critics, of course, push back. They argue that observation doesn't require a conscious mind, just an interaction with another particle or detector. A photon hitting a camera sensor is enough to collapse a wave function, no human needed. But even this pragmatic view doesn't fully resolve the mystery. Why should reality hinge on interaction at all? Why doesn't the universe simply exist in a definite state from the start? The implications ripple outward. If observation influences reality at the quantum level, could it also play a role in the universe's larger structures? Some theorists speculate that consciousness might be entangled with the cosmos in ways we don't yet understand, acting as a kind of feedback loop that stabilizes existence. Others propose that the observer effect is a clue to a deeper truth, that the universe is fundamentally participatory, a dance between what is and what is perceived. Whether consciousness is a key player or just a bystander, one thing is certain: the observer effect shatters our classical intuition about how reality works. The universe isn't a static backdrop, it's dynamic, responsive, and perhaps even waiting for us to look before it decides what it wants to be, and that changes everything. Chaos isn't just randomness, it's the universe's hidden choreography. Take a single butterfly flapping its wings in Brazil, and weeks later, a storm brews over Texas. That's chaos theory in action, tiny, unpredictable ripples cascading into monumental changes. Yet, against this backdrop of perpetual turbulence, the cosmos hums with stunning regularity. Planets orbit on schedule, galaxies spin with precision, and atoms bond in perfect harmony. How can a universe built on chaos also be a clockwork of order? The answer lies in the delicate interplay between these two forces, a dance so finely balanced that even the slightest misstep could unravel reality itself. Consider the solar system. For centuries, astronomers believed it was a model of predictability, a celestial machine where every planet's motion could be calculated centuries in advance. But chaos theory shattered that illusion. Even with Newton's laws, the gravitational tug of war between planets introduces tiny uncertainties, errors that compound over time. A slight nudge to Jupiter's orbit today could send Mars spiraling out of the solar system millions of years from now. And yet, despite this inherent instability, the solar system has endured for billions of years. Why hasn't it torn itself apart? The secret lies in dynamical stability, a kind of cosmic shock absorber that dampens chaos just enough to prevent catastrophe. Orbits aren't rigid tracks but flexible loops, subtly adjusting to perturbations without collapsing. It's like a spinning top that wobbles but never falls. Chaos is present, but it's kept in check by deeper, self-correcting rhythms. Zoom out to the grand scale of the universe, and this balance becomes even more astonishing. The cosmos began in a maelstrom of quantum fluctuations, a seething soup of particles popping in and out of existence. From that primordial chaos, structure emerged: galaxies, stars, and planets, not despite randomness, but because of it. Tiny density variations in the early universe, magnified by gravity, became the seeds for everything we see today. Without those initial irregularities, matter would have spread too evenly, and the universe would be a featureless void. Chaos, in other words, is the sculptor of order. But the dance doesn't end there. Look at Earth's climate, a system where hurricanes, droughts, and ocean currents all stem from chaotic interactions. Yet, over millennia, the planet maintains a relatively stable temperature range, allowing life to thrive. Or consider your own heartbeat, a rhythm governed by electrical impulses so sensitive that a single misaligned ion channel can trigger a arrhythmia. Yet your heart keeps beating day after day in a precarious but persistent order. The unsettling truth is that chaos and order aren't opposites, they're partners. One without the other leads to collapse. Too much chaos, and the universe dissolves into noise. Too much order, and it becomes a static, lifeless crystal. The sweet spot between them is what allows complexity to emerge, from swirling galaxies to the neurons firing in your brain. So does this delicate dance keep reality from unraveling? Perhaps. the universe isn't a machine that runs flawlessly, nor is it a storm of pure chance. It's something far more fascinating, a self-regulating system where chaos and order push and pull, each tempering the other's extremes. And in that tension against all odds, existence finds its footing. Our brains are exquisitely tuned survival machines, but they weren't built to perceive reality as it truly is, only what helped our ancestors avoid predators and find food. Think of it like a radio tuned to a single station. We're only picking up the frequencies that matter for survival, while the rest of the cosmic broadcast fades into static. Take color, for example. The human eye detects just a sliver of the electromagnetic spectrum, what we call visible light. Meanwhile, the universe hums with gamma rays, radio waves, and X-rays entirely invisible to us. A bee sees ultraviolet patterns on flowers. A rattlesnake senses infrared heat signatures. Each creature inhabits its own sensory world, none more real than the other. So what if the answer to existence isn't hidden in the equations we've written, but in dimensions or phenomena we lack the hardware to detect? Consider gravity. We feel its pull, measure its effects, but no one actually knows what it is. Einstein described it as the curvature of space-time, but that's a model, not an explanation. Could gravity be leaking into our three-dimensional world from a higher dimension we can't perceive, like shadows cast by objects in a fourth spatial dimension? String theory suggests this might be the case, that what we experience as gravity is just a feeble echo of interactions happening in a realm with 7 or more dimensions, curled up smaller than an atom. It's like trying to understand a symphony by listening through a keyhole. You'll catch fragments, but never the full score. Then there's dark matter, which outweighs visible matter 5-to-1, yet remains utterly invisible to every telescope and detector we've built. We know it's there because galaxies rotate faster than they should. But what if it's not just an unknown particle? What if dark matter is the gravitational fingerprint of parallel universes stacked alongside ours in higher dimensions, worlds so close yet forever beyond our reach? The idea isn't pure speculation. In certain brain cosmology models, our universe could be a three-dimensional membrane floating in a higher dimensional bulk, with dark matter's gravity bleeding through from neighboring brains. Even time might not be what it seems. We experience it as a relentless, one-way flow, but physics treats it as just another dimension, a coordinate that could, in theory, be traversed like space. What if our linear perception of time is as limited as a flatlander's understanding of height? Some interpretations of quantum mechanics suggest that at the fundamental level, time doesn't pass at all. That past, present, and future exist simultaneously in a block universe, and our sense of now is just a cognitive illusion. If true, the question, why does the universe exist, might be as nonsensical as asking why a mountain exists. It simply is eternally, in the grander structure of reality. The most humbling possibility, our brains might be hardwired to misunderstand the cosmos entirely. Neuroscience shows we don't experience raw reality, but a heavily processed simulation constructed by our senses and neurons. Colors, sounds, even the solidity of objects are mental constructs, useful fictions that keep us alive. Quantum mechanics already reveals a world where particles exist in multiple places at once until observed, where entanglement links particles across light years instantly. These aren't just weird facts, they're clues that reality operates on rules our primate brains didn't evolve to grasp. So where does that leave us? Chasing the universe's secrets with tools designed to hunt antelope and avoid snakes. Maybe the answer to existence isn't a missing equation, but a missing sense, a way to perceive the dimensions, forces, or layers of reality that lie just beyond our cognitive horizon. Or perhaps, like ants trying to comprehend the internet, some truths are simply unfathomable within the confines of our current minds. Either way, the universe owes us no obligation to make sense. And that's what makes the search so thrilling. Imagine a person who looks like you, talks like you, even reacts to pain or joy just like you, but behind their eyes there's nothing. No inner world, no experience of color or sound, just an empty shell going through the motions. Philosophers call this thought experiment the zombie problem. And it's not about horror movies, it's a razor-sharp tool probing one of existence's deepest mysteries. Why does consciousness exist at all? At first glance, the idea seems absurd. How could something act exactly like a human without any inner experience? But consider your smartphone. It can recognize your face, respond to your voice, even mimic conversation, yet no one would argue it's conscious. The zombie argument pushes this further. If a being could perfectly replicate human behavior down to the atomic level, indistinguishable from the outside, what proof do we have that consciousness isn't just an illusion, a ghost in the machine? This isn't just wordplay, it cuts to the heart of the hard problem of consciousness, coined by philosopher David Chalmers. Physics can explain how neurons fire, how the brain processes information, but it hits a wall when explaining why any of that should feel like something. You don't just detect light, you see crimson sunsets. You don't just process sound, you hear music that gives you chills. This gap between objective mechanics and subjective experience is where the zombie problem thrives. If a universe can produce beings that behave exactly like us without consciousness, why did evolution bother with inner experience at all? Some theorists argue consciousness is an accidental byproduct, like the heat from a light bulb, useless but unavoidable. In this view, zombies could exist, and we're just lucky or unlucky to be stuck with the glow of awareness. Others, like panpsychists, flip the script entirely. They propose consciousness is a fundamental property of the universe, like mass or charge, present even in atoms. In this framework, zombies are impossible because even the simplest particles have some rudimentary form of experience. Then there's the wild card, quantum consciousness theories. A handful of scientists speculate that microtubules in brain cells might exploit quantum effects to generate consciousness, making it a physical process too delicate to replicate artificially. If true, zombies wouldn't just lack inner experience, they'd collapse under the weight of their own incoherence, like a computer trying to run a program written in smoke. The zombie problem forces us to confront an unsettling possibility. Consciousness might not be necessary for the universe to function. Stars could burn, planets could orbit, and perfect zombie copies of humanity could debate philosophy, all without a single glimmer of inner light. But if that's the case, why does our version of reality include this vivid, undeniable sense of being? Is it a fluke or a clue that subjectivity is woven into the fabric of existence itself? The answer, if there is one, might not just explain minds, it might redefine reality. What if you could cheat death not through medicine or luck, but through the sheer mathematics of quantum mechanics? That's the unsettling premise of the quantum suicide thought experiment, a mind-bending scenario where survival isn't just probable, it's guaranteed. Picture this. You're strapped into a machine rigged to a quantum trigger, like the spin of an electron. Each time you pull the lever, there's a 50% chance the device releases a lethal pulse or does nothing at all. In a single universe, this is Russian roulette with cosmic odds. But in the many worlds interpretation of quantum mechanics, where every possible outcome spawns a new reality, something extraordinary happens. From your perspective, you'd never experience death, only the branches where you survive. Here's why. Every time the trigger is pulled, reality splits. In one timeline, the device fires and your story ends. but in another it doesn't, and you continue. To an outside observer, the odds are grim over time. Most versions of you perish, but from your subjective viewpoint, you'd only ever find yourself in the realities where the gun never fires. It's like flipping a coin and always landing on heads, not because the coin is rigged, but because every tails result happens in a universe you're no longer part of. You become, in effect, immortal by statistical inevitability. This isn't just a macabre party trick, it's a profound challenge to how we understand existence. If consciousness truly branches with every quantum decision, then the fact that you're here to ponder this question isn't random. It's the only possible outcome you could experience. The implications ripple outward. Does this mean life itself is a self-selecting process, where sentient beings inevitably find themselves in realities where their survival is possible? Some theorists take it further, suggesting this could explain the fine-tuning of the universe, not because the constants are magically perfect, but because conscious observers only arise in the rare branches where they can. Of course, the experiment raises ethical and practical nightmares. No one's volunteering to test it, and for good reason. But the thought experiment itself is a lens, forcing us to confront the stranger corners of quantum theory. If reality is a tapestry of infinite branching paths, then death might not be an absolute, just a road you never walk down. And that's either the most comforting thought imaginable or the most isolating. After all, in a multiverse where every possibility plays out, you're not just lucky to be alive, you're inevitable. The universe shouldn't be here, at least not like this. According to the brutal math of thermodynamics, randomness should reign supreme, a featureless sea of particles spread thin, where nothing ever clumps, nothing ever changes, and time itself becomes meaningless. This is the Boltzmann Universe, a nightmare of perfect entropy named after the 19th century physicist who first grappled with its implications. Yet when we look around, we see galaxies swirling, stars igniting, and planets teeming with complexity. How did our cosmos cheat the odds? Start with entropy, the universe's relentless slide toward disorder. Picture a sandcastle on a beach left alone. Wind and waves will scatter it into shapeless grains. Given enough time, every structure succumbs to this fate. The Boltzmann universe takes this to its logical extreme. Over infinite time, every possible arrangement of particles should arise purely by chance. Most of those arrangements would be chaotic noise, but occasionally, very occasionally, a pocket of order would flicker into existence. A single hydrogen atom here, a fleeting snowflake there. And once in an unimaginable eternity, a fully formed brain might pop into being, complete with false memories of a past that never was. By this logic, Boltzmann argued, the most probable universe isn't one filled with galaxies and life. It's a vast, dead void where ordered structures are vanishingly rare mirages. Yet here we are, surrounded by structure at every scale. The cosmic microwave background, the afterglow of the Big Bang, shows a universe that's suspiciously smooth but dotted with tiny fluctuation seeds that grew into the galaxies we see today. If the cosmos were truly random, those fluctuations should be wildly uneven, like static on a broken TV. Instead, they follow a pattern so precise it hints at something deeper at work. One escape hatch is the idea that our universe hasn't existed long enough to reach maximum entropy. The Big Bang might have started the clock in an unusually low entropy state, like winding up a toy before letting it run down. But this just pushes the mystery back a step. Why was the early universe so ordered to begin with? Some theorists propose inflation, the exponential expansion of space in the first fractions of a second, stretched quantum jitters into cosmic scale structures, like blowing up a fingerprint to the size of a continent. Others suggest gravity, the great organizer, fights entropy's spread by pulling matter into galaxies and stars, creating pockets of order in a sea of chaos. Then there's the multiverse angle. If countless universes bubble up from a quantum foam, most might indeed be Boltzmann nightmare static, lifeless voids. But a rare few, through sheer luck, could land in states where entropy starts low and structure emerges. We'd find ourselves in one of those outliers not by chance, but because it's the only kind of universe where life can arise to ask the question. But perhaps the boldest answer is that the Boltzmann universe isn't wrong, it's incomplete. Modern physics reveals that particles don't just move randomly, they obey quantum laws that inherently resist disorder. Entanglement links particles across space, creating correlations that entropy can't easily undo. Dark energy stretches the cosmos, preventing matter from clumping too quickly. Even the arrow of time itself, which points toward disorder in our everyday experience, might be an emergent property of deeper, hidden symmetries, the real takeaway. Our universe isn't defying statistics, it's rewriting them. What looks like a miracle of order might be the inevitable outcome of laws we're still uncovering. And that's either the most comforting thought imaginable or the most unsettling, that the cosmos isn't balanced on a knife's edge between existence and chaos, but is instead unfolding exactly as it must. Mathematics isn't just a tool, it's the universe's secret language. Every spiral galaxy, every vibrating atom, even the way light bends around a star follows equations scribbled in the cosmic ledger long before humans existed. But here's the mystery. Is math something we discovered, etched into the fabric of reality itself? Or is it a brilliant invention, a lens we crafted to make sense of the chaos? The answer might redefine what existence even means. Take the Fibonacci sequence, a pattern where each number is the sum of the two before it. It appears in sunflower seeds, hurricane spirals, even the branching of galaxies. Or consider pi, the ratio of a circle's circumference to its diameter, a number that shows up in ripples on a pond and the orbits of planets. These aren't just handy calculations, they're woven into nature's blueprint. Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics, the eerie way abstract equations predict real-world phenomena with pinpoint accuracy, like a key fitting a lock we didn't know existed. But if math is universal, why does it feel so human? Ancient civilizations developed different number systems. Babylonians used base 60, the Maya base 20, yet all eventually converged on the same underlying truths. 2 plus 2 equals 4, whether you're counting coconuts or cosmic rays. This suggests math isn't arbitrary but uncovered, like chiseling a statue from marble. Even stranger, some mathematical concepts, like imaginary numbers or non-Euclidean geometry, were dismissed as pure fantasy until we found them governing quantum mechanics and the curvature of spacetime. It's as if the universe had the answers all along, waiting for us to ask the right questions. On the other hand, math could be a mental scaffold, a game of symbols and rules we invented to tame the wilderness of experience. Think of chess. The rules are human-made, but players discover strategies within them. Similarly, math might be a self-contained system that happens to mirror reality because we built it to do so. After all, we don't ask if the alphabet is real. It's a tool for capturing ideas. Maybe math is the same, a glorified notation system that evolved alongside our brains. Yet this raises a paradox. If math is purely invented, why does it describe black holes or DNA so flawlessly? Why do alien civilizations, if they exist, likely share our grasp of prime numbers and gravitational equations? The answer might lie in the middle. Math is a dialogue between mind and cosmos, Our brains evolved to recognize patterns, and the universe is pattern-rich. Math could be the overlapper, a shared territory where human logic and cosmic order meet. The stakes are higher than they seem. If math is discovered, the universe is fundamentally logical, even intelligible. If invented, reality might be stranger than math can ever capture. Either way, one thing's certain: every time we solve an equation, we're not just doing homework, we're eavesdropping on the universe's deepest conversations. Consciousness is the one thing we can't escape, the raw, undeniable fact that it feels like something to be alive. You don't just process light as wavelengths, you see the fiery hues of a sunset. You don't just decode sound vibrations, you hear the ache in a loved one's voice. This is the hard problem of consciousness, a puzzle so profound that even our most advanced neuroscience barely scratches its surface. We can map neurons firing, trace neurotransmitters, and link brain regions to emotions, but none of that explains why any of it should come with an inner movie playing in your mind. Take color, for example. Science can describe how light at 700 nanometers hits your retina, triggering a cascade of electrical signals to your visual cortex. But nothing in that chain of events explains why you experience the color red as red, a vivid, qualitative sensation that no microscope could ever detect. Philosopher David Chalmers, who coined the term hard problem, likens it to explaining how a computer could feel joy just by studying its wiring. The gap between physical processes and subjective experience isn't just wide, it's conceptually bottomless. This isn't just philosophy. The hard problem forces us to confront a radical possibility. Consciousness might not be a byproduct of the brain, but something more fundamental, woven into the fabric of reality itself. Some theories, like panpsychism, suggest even atoms or particles might have a rudimentary form of experience, not thoughts or feelings, but some infinitesimal spark of subjectivity. If true, then human consciousness isn't a miracle but an amplification of something latent in the universe, like waves rising from an ocean of tiny ripples. Others propose even wilder ideas. Integrated information theory argues consciousness arises from the complexity of connections within a system, meaning sufficiently advanced networks, whether biological or silicon, could develop their own inner worlds. Then there's the orchestrated objective reduction theory, which ties consciousness to quantum processes in the brain's microtubules, suggesting our minds might literally dance on the edge of the quantum and classical worlds. But here's the real kicker. If consciousness is fundamental, it could explain why the universe seems so finely tuned for awareness. The constants of physics, the structure of atoms, even the existence of time, all might be prerequisites not just for life, but for experience itself. In this view, the universe isn't just a cold, mechanical clockwork. It's a stage set for observers, a cosmic experiment in what it means to be. The hard problem doesn't just challenge science, it redefines what we think reality is. Whether consciousness is an emergent illusion or a bedrock feature of existence, one thing's certain: the fact that we can ponder it at all is the greatest mystery of all. The universe is playing a game with no reset button, and the rules are written in fading ink. Scientists have sketched 3 possible endings, each more unsettling than the last. The first, the Big Crunch, imagines gravity finally winning its cosmic tug-of-war. After billions of years of expansion, the universe would slow, stop, and reverse, galaxies rushing back together in a nightmarish rewind. Stars would collide, black holes merge, and eventually, all matter collapses into a singularity hotter and denser than the Big Bang itself. It's a fiery bookend to existence, where time and space crumple like paper tossed into a furnace. Then there's heat death, the opposite extreme. Here, the universe keeps expanding forever, but dark energy, the mysterious force accelerating that expansion never relents. Galaxies drift so far apart that their light can never reach one another. Stars burn out, black holes evaporate, and particles spread so thinly that temperatures approach absolute zero. The cosmos becomes a vast, silent graveyard where even atomic motion grinds to a halt. Time loses all meaning because nothing ever changes again. But the strangest possibility lies between these extremes, the Big Rip. If dark energy grows stronger over time, it could eventually overpower gravity, electromagnetism, even the nuclear forces holding atoms together. First, galaxies would shred. Then stars, then planets. In the final moments, atoms themselves would be torn apart, their quarks scattered across an infinite void. It's not just the end of life, it's the end of physics itself. What makes these scenarios so haunting isn't just their inevitability, but their implications. If the universe is doomed to collapse or freeze, its current stability becomes a fleeting miracle. We're living in a cosmic springtime where galaxies still shine and chemistry still works, but winter is coming. The odds of existing in this narrow window, rather than the endless cold or crushing heat that follows, are vanishingly small. Yet there's a twist. Some theories suggest our universe might not be a one-way trip to oblivion. In cyclic cosmology, the Big Bang wasn't the beginning, just the latest bounce in an endless cycle of expansion and contraction. Each iteration leaves traces in the next, like echoes in a cave. String theory takes this further, proposing higher dimensional membranes colliding to birth new universes endlessly. Even heat death might not be final. Quantum fluctuations could, over unimaginable timescales, spawn new Big Bangs, like bubbles forming in a lifeless sea. The real question isn't just how the universe ends, but what its fate says about meaning. If everything vanishes, does that make life a brief spark in the dark? Or does the very improbability of our existence against such odds make it more precious? The answer might lie not in cosmology, but in us. The universe doesn't need to be eternal to matter. It just needs observers to wonder, however briefly, why it's here at all. And that's a mystery no final freeze or crunch can erase. Einstein's relativity and quantum mechanics revolutionized physics, but they're fundamentally incompatible, like two masterpieces painted in clashing styles. This cosmic standoff has forced physicists to explore radical alternatives, theories so daring they rewrite the rules of reality itself. Loop quantum gravity, for instance. Imagine spacetime not as a smooth continuum, but as a fabric woven from tiny, indivisible loops. Think of the universe as a mesh of interconnected threads, where even time is stitched together in discrete steps. This could solve the singularity problem at the heart of black holes, replacing infinity with a tightly woven knot of quantum threads. But here's the catch: if spacetime is granular, why does it feel so seamless to us? The answer might lie in scale. Just as a movie appears fluid despite being made of individual frames, our perception smooths over the universe's underlying pixelation. Then there's emergent spacetime, the idea that space and time aren't fundamental but arise from something deeper, like temperature emerging from the motion of atoms. Imagine a crowd at a concert. From a distance, you see waves of movement, but up close, it's just individuals shifting position. In this view, spacetime could be a collective illusion, a holographic projection of quantum entanglement. The math even suggests that the three-dimensional world we experience might be encoded on a distant, two-dimensional surface, like a cosmic DVD storing the data for our reality. It's a theory that turns the universe inside out, suggesting that the solid ground beneath your feet is no more substantial than a shadow on a cave wall. But perhaps the most provocative contender is causal dynamical triangulation. which treats spacetime as a patchwork of tiny, geometric shapes that glue themselves together dynamically. Picture a child building a castle from blocks. Each block represents a unit of spacetime, and the way they fit together determines the universe's structure. Unlike loop quantum gravity's loops or string theory's vibrating strings, this approach relies on simplicity, no extra dimensions, no hidden variables. Yet it still manages to generate a four-dimensional cosmos from scratch, complete with gravity and quantum effects. The catch: it requires time to be fundamental, not emergent, a direct challenge to relativity's flexible clock. These theories aren't just academic exercises, they're attempts to answer why the universe defies its own odds. If spacetime is emergent, its apparent fine-tuning might be a side effect of deeper laws, like how water's surface tension emerges from molecular forces. If it's granular, the Big Bang could have been a quantum leap in a pre-existing network, not a true beginning. And if causality is the bedrock, then the universe's improbable stability might be baked into its very architecture. The irony is delicious. The very theories trying to unify physics often feel like they're describing different universes altogether. But that's the point. Reality doesn't owe us intuitive explanations. Whether it's loops, holograms, or geometric blocks, the true test isn't which idea feels right, it's which one survives the brutal courtroom of experiment. And until then, the universe's greatest trick remains convincing us it should exist at all. From fine-tuning to quantum mysteries, the question, why shouldn't the universe exist, isn't just a scientific puzzle, it's a mirror held up to the very nature of reality. Every law, every constant, every fleeting quantum fluctuation seems to balance on a knife's edge, where even the slightest shift would unravel everything. Stars wouldn't ignite, atoms wouldn't bond, life wouldn't stir, yet here we are, breathing, thinking, wondering how it's possible at all. The multiverse offers one escape hatch, a cosmic lottery where infinite universes flicker in and out of existence, most doomed to silence, and ours just happen to hit the jackpot. It's a comforting thought, in a way, no miracle, just statistics. But then, why does it feel like cheating? If every possible universe exists, does that make ours less special or more? The simulation hypothesis flips the script entirely, suggesting the universe's perfection isn't luck but design, a programmed reality where the constants are dialed in by some advanced civilization. It's a modern myth, but one that lingers because it taps into a deeper unease. What if the universe isn't just improbable, but impossible without unseen architects? Then there's the third path, the one that keeps physicists awake at night. Maybe we're missing something fundamental. The fine-tuning problem, the mystery of consciousness, the enigma of quantum entanglement. These might not be puzzles to solve, but clues to a bigger picture. Perhaps the universe isn't fine-tuned because of luck or design, but because the very question is backward. What if the laws of physics aren't arbitrary rules, but the only possible outcome? The inevitable result of deeper principles we haven't uncovered yet. String theory's hidden dimensions, the holographic principle's shadow codes, even the eerie symmetries of particle physics, all hint that reality might be far stranger and more interconnected than we've dared to imagine. The search for answers isn't just about satisfying curiosity, it's about redefining what it means to exist. Every time we probe the cosmos, we're not just uncovering its secrets, we're unraveling our own place within it. The universe shouldn't exist, and yet it does. That paradox isn't a dead end, it's an invitation. An invitation to question, to explore, to marvel at the fact that against all odds, we're here to ask the question at all. So what do you think? Is the universe's existence a statistical fluke, the work of unseen hands, or something beyond our current grasp? Drop your thoughts in the comments below, and if this journey through the cosmic unknown left you as awestruck as it did us, don't forget to like, subscribe, and hit that notification bell. Because the universe might be improbable, but the next mind-bending revelation, that's just around the